Good morning. Are there any questions before we get started? Yes?
We don't have class on Thursday, so we're not going to be able to right?
You don't have section on Thursday. Yeah, that's right. Right, that's right. Although, so I'm, right after class, I'm rushing out to get on a plane. I won't be back till Thursday. And Mike has graciously agreed to teach a lecture on Wednesday. And on Friday, I will be teaching, and because I won't be here to hold my office hours on Wednesday and Thursday, I will hold office hours here in this room right after class for an hour from 10 to 11 on Friday, because there is no lecture in this room after us on Fridays. There is on Mondays and Wednesdays, but not on Fridays. And that might be a very good time to, for if you have any questions for your group, that might be a good time to bring them. Yes? The homework's due Friday at 5. And so you can slip it under my door before Friday at 5. So on BSpace, I've created a forum for the project, and there's separate topics for each particular project topic. So these will be shared by the groups that have the same project topic. So please post questions there as they come up, and I will be looking for questions over the next few days and obviously till the end of the semester, but we'll be sure to respond to them. In addition, under resources, I've created a separate area called projects, and within that there are separate folders for each of the topics as well. And in the next couple days, I'll be putting up references and things that I find that it would be relevant to the various projects, such as background data, information about some of the variables for some of the different projects. And if there's anything in particular you have a question on that, in terms of getting help of finding background material, if you post that under the forum, then I can answer it there and possibly also post something under the resources section. All right, today is going to be formally the last day that we're going to speak about sampling, and so we're essentially going to wrap up with a few sort of loose ends and things that were already raised by you on Friday, some questions about sampling in particular. So there are 3 or 4 separate topics here. The first one is non-probability samples, and I wanted to make sure that we talked about those specifically. Here's an example of one. It's ask the person on the street. You see a lot of this in news shows, on the radio, etc., where the man on the street, the woman on the street, what do you think? And here's a set of people on the street that I have pulled together. So this is definitely not a probability sample in that we don't have some sort of list of all the possible units that would be in our target population, and we're not using a random chance process to select people. We're just simply approaching people. And if you look at these, I think some people look more approachable than others, like the guy in the middle with the sunglasses, as opposed to the one with the crown on her head. And the question is like, who would you approach? And can you imagine how biases might arise in whatever opinions or information you collect from the person on the street if you're trying to make some inference about the population? So non-probability samples, such as choosing a man on the street, or the height report, where you mail out the surveys to these women's centers and allow people to elect to respond or not. These are samples of convenience. They were not the subjects that are in your sample were not chosen by you by a chance process. They might have been chosen by you, but not by a chance process. These samples of convenience can often come along with lots of bias. So selection bias in particular, sort of the bias that you would get in terms of coming from the way you select someone to be in your sample. Okay, so basically we've studied 3 different kinds of bias, or mentioned 3 different kinds of bias. One was measurement bias, which can arise from the specific questions or measurements that you take on the units in your sample. And this one is selection bias. And then another one, a third one that we've discussed is non-response bias. So when we look at our target population versus our sampling frame, and within our sampling frame there's our sample population, and then there's that little bit of the folks that are in the sampling frame, but we can't still, and are in the target population, but we can't get hold of them, and those are might lead to non-response bias. Okay. Just so you don't go away thinking that the only way to take a sample that involves a chance process, I want to introduce 2 other ways of sampling, and this is particularly relevant to the folks who are doing the Radon project. 2 other ways of doing random sampling other than the simple random sample. So here's one example of, I'll give an example for each of the 2 ways. The first one is a survey of cows. The actual observation unit that we're going to take measurements on is a cow, and we're interested in the health of dairy cows. Now, what we actually have are a bunch of farms, and we're going to take a simple random sample of these farms. There are 11 farms here. We're going to take a simple random sample of 3 of these farms, and those are the 3 that I chose. And then we go to each of those farms and get permission to look at the cows. And let's not worry at this point about non-response bias. And so what we do is we actually sample and take measurements on all the cows at each of the farms. So is this a simple random sample of cows? It's not. Why not? Somebody said no. Yes?
You're not taking samples from each farm?
That's right. You're not taking a sample of cows. That's right. And so if it were a simple random sample of cows, you wouldn't expect to get all the cows from one farm. It is a simple random sample of farms. So this is an example of cluster sampling, where the cows are clustered together according to what farm they're on. And then we take a simple random sample of the clusters, and then all the units that belong to each of the clusters will be in our sample. So it's still a probability sample, but it's not quite the same as what we're used to. So the observation unit is the cow. Yes?
Would that be a form of blocking to compare the older data out there?
Well, actually, the next example that I'm going to show you is one of blocking. And it's good that I'm glad you're looking at the parallels between using chance in design of experiments and using chance in survey sampling, because there are parallels. This isn't quite that. And you'll see the next one will be like that. So the observation unit is a cow. The sampling unit is a farm. We take a simple random sample of the farms, and these are our clusters. Because we take measurements of all the cows at the farm, that's called cluster sampling. So we can actually answer the question of what's the chance that a particular cow is selected. So here we have our 11 farms. We take a simple random sample of 3, and we could point to a particular cow, like this one, with a green circle, and say, what's the chance this cow is included in the sample? So does anybody know what's the chance that that cow would be included in our sample? Yeah?
Would it be 1 out of 11 because you're sampling farms, and each farm you sample every cow?
It's close. Yes, 11's the denominator, and it's because it's related to just sampling farms. If we pick that farm that the cow belongs to, that cow will be in our sample. Since we're taking 3, it's 3 out of 11. But yes, that's the right idea. So, so that the chance that a particular cow is included in the sample is simply the chance that that cow's farm is included in the sample. So there's still a probability mechanism going on here, and we can still create estimates for the entire population of all cows, and we can still attach errors to our estimates. It becomes a little trickier now because we no longer have a simple random sample of the actual units that we're taking the measurements on. So it becomes a little trickier finding what the standard error is for our estimates, and we're not going to go into that in this class. There's a whole advanced upper division class called Stat 152, Concepts in Survey Sampling and Design of Experiments, that goes into that sort of detail. All right, second approach, emergency room survey, where the observational unit is an emergency room, and we're interested in the quality of treatment at these emergency rooms all across the United States. So our target population are all emergency rooms in the United States. So here's the United States. You see, well, minus Alaska and Hawaii. And here's the continental or contiguous states. And we want to take a sample of emergency rooms. But suppose that we want to make sure that we are able to provide information to each state about the treatment that patients receive in emergency rooms in their state. That means we want to make sure that we get samples of emergency rooms from every single state. So this is hypothetical, just like the previous one. And here I'm saying every dot across the 48 states represents an emergency room. So this is a hypothetical set of emergency rooms. And the idea is that we want to make sure that every state has a sample within it. So what we do is we take a simple random sample within each state. So we go to every state. For example, here's the state of Nevada. We see that there are 17 emergency rooms in that state, and then we take a simple random sample from those 17. So the green dots represent represent the emergency rooms that have been sampled. And notice every state has at least one green dot in it, and that's because we're sampling from every single state. If we were to take a simple random sample of all emergency rooms from across all the states, it could wind up where a state such as Maine, which doesn't have very many, has no samples or no units in our sample. So if we take a sample of size 6 from Nevada, and I look at any particular emergency room, I can answer the question, what's the chance that this particular emergency room was selected for the sample? And that we can answer, and that's in a frame that we're used to working with because it's within using simple random sampling. Now going back to your question, do you see how this might be related to blocking? So we can think of every state as a block where there might be rules and regulations, laws that are particular to the state. And so we've split the emergency rooms up into groups that are similar. And those groups are the states. And then we take samples from each state. So that is similar to the concept of blocking. Okay, so in this case, we divide up our target population into groups. These are non-overlapping groups. So it's like a partition of all the possible units in our target population. And then we go and we take a simple random sample from every single one of these. This is called stratified sampling. Each group is a stratum. So a state in the previous example was a stratum. That's singular. The strata are plural. So all the states together are the strata in our target population. Why would anybody want to take a stratified random sample? Well, if we think back to blocking, it was why do you block? You might block if you are able to divide the units up into groups that are as similar as possible and then different from the other groups. In which case, you can by making sure that you sample from each of these groups, you can get a much better estimate of the overall population if you're sampling from each one of these groups. The other is if you want to, and that's the example that I gave you, if you want to make sure that you can give an estimate, a decent estimate for each of these strata. So in Nevada, you want to go to them and say, we took a simple random sample of emergency rooms from your state, and these are the results we found. You need to have a stratified sample in order to ensure that you can have confidence intervals for your estimates that are reasonable confidence intervals because you have a large enough sample. So those are the two concepts of types of probability sampling other than simple random sampling. You can see simple random sampling in each one of these. That concept's there, but it's not entirely the same. In cluster sampling, you've grouped your samples into, typically they're small groups in your clusters, and you take a simple random sample of clusters, and once you have a cluster, you look at everybody in that group. Stratified sampling, you also divide it up into groups, non-overlapping groups. Then from every single stratum, you take a sample, a simple random sample. Okay? Other questions on that? So again, you can provide, with stratified sampling, you can provide estimates for each, possibly depending on the size of your sample. You can possibly provide an estimate for each stratum, but you can also pull together all the results you have and provide an estimate for the total target population. Those of you who are working on the Radon project, it's a stratified sample. What are the strata? Is anybody here working on Radon? Have you gotten that far to figure out what are the strata? The stratas are the counties. So there's a there's a simple random sample of households within every single county in Minnesota. Alrighty. Let's go back to the simple random sample. So the first two topics, one was talking about non-probability samples. And the next one was talking about two kinds of probability samples that still use simple random sampling, but not in the traditional way, sort of extensions of simple random sampling. And now we're going back to the simple random sample and talk about questions such as, how big should my sample be? As there were a couple of people that had some very good observations on Friday. And in fact, some of your homework is exactly related to the observations that they were making. So recall the formula that we derived on, not the, on homework number 5, on what's the error associated with simple random sampling. And so in particular, we wanted to know what's the error of a sample average or a sample count. Because we now know what the probability distribution is for these and from that probability distribution, you can exactly derive these. This is derived in more advanced classes such as Stat 134 and Stat 135. In this class, we sort of derived it. We showed that it was the case by plotting those curves through the points where we had actually been able to figure out the standard deviation for a count or an average. So the formula is it's the population SD. That's the SD of the box. That's what's the spread of individual observations about the mean, divided by the square root of the sample size, that's small n, then times the finite population correction factor. That's the factor that corrects for sampling with and without replacement. If that square root of capital N minus little n over capital N minus 1, we can remove that. If we were to remove that, that would be the standard deviation of the sample average for sampling with replacement. So that's why it's called the finite population correction factor. If you had an infinite population, it wouldn't matter if you were drawing with or without replacement. It would all be the same. So that's why it's called finite population correction factor. Okay, so here's two scenarios. Same size of population, 10,000 total units in my target population. Two different sample sizes, 100 versus 400. Finite population correction factor, what's the difference between a sample of 100 versus a sample of 400? We see that the FPC, I've calculated for you, is 0.995 in 100 and 0.980 for 400. So you can see that finite population correction factors are very similar, and that's because our population size is so large compared to our sample size. So how accurate might our sample average be, or is our sample average? If we go to make an estimate for our population average, and when we want to create a confidence interval, or we want to say, here's my estimate for the population average, and here's the error that's attached to my estimate. There's our formula again. This time I've plugged in what the square root of n is. It's 10 versus 20. So when you look at these things, what's driving your decision about the sample size? Is it the FPC? Is it the sample size itself in absolute terms? So is it the size of the sample relative to the population, or is it the size of the sample itself? Jeff? When the population's really large, it's just the size of the sample. And what's the factor? Right, meaning I have quadrupled my sample size. And what happens to my error when I quadruple my sample size? By how much?
By 0.01.
Now what's really going on here? What's driving the standard errors? This is divided by 10. This guy's divided by 20. So the difference between the 0.995 and the 0.980 is really tiny, nearly negligible. The big difference between those two is what? Yes? Yes, that's right, the denominator, which is the number of draws. And what happens to those two? What's the difference between them? I've taken a sample four times. The one on the right is 4 times the one on the left. And it's cut in half. And that's because of the square root. So I take a sample 4 times as large. The accuracy shrinks by half because of the square root. Okay? And the FPC, those stay roughly the same. So that was one of the questions I think that some of you were asking on Friday. Here's another scenario. Here's where I'm keeping the sample size the same. And I look at a population of 10,000 versus 100,000. So we've already heard your comments about that what really matters is the actual size of the sample compared as opposed to the fraction of the sample you're drawing. So many times you hear people say, oh, look, the population is 10 times as big. So in order to get an accurate sample, an accurate estimate for my population, I need to take 10 times as many samples. And you look at this and you see here we're keeping the sample size the same, n is 100. Look at the difference between the finite population correction factors, 0.995 versus 0.99995. And the accuracy of our averages, in this case, is the population SD divided by 10 times 0.995. And in the 100,000 population, it's a population SD divided by 10 times oops, I lost a 9, 0.99995. So it shows that even when we get a really much larger population, 100,000 versus 10,000, the accuracy of your estimate is really about the same as long as our fraction of the sample size to the population size is not very big. So the finite population correction factor we can often just ignore as in this case, it's probably ignorable. And what's driving the standard error, or the accuracy of our estimator, is the absolute size of the sample. And we see that they're both dividing the population SD by 10. Questions on that? Because we're about to go to yet another round of comparing SDs. Okay, sometimes we're asked to, when we're asked to try and figure out, before we ever take our sample, we need to know, well, how large a sample should we take? And sometimes our goal is to say, well, we want our confidence interval or our error to be a certain width. And that can be said in absolute terms. Like, I'd like my confidence interval to be 2 percentage points wide if we're looking at estimates of population percentages. Or we sometimes would like it to be relative to the mean. So I'd like it to be 1/10 of the mean. And so here are two scenarios, and this is what you were asking at the end of the day, is I want to estimate a population proportion. And I really don't know what that is, but I might have a sense of whether it's something very rare, like a very rare disease, or if it's something really common. So in my one case, I'm saying my rare has, I think, roughly 4% of the population's being affected, and something that's common, roughly 40% of the population's being affected. So the question is, well, how big a sample should I take if I want to come up with accurate estimates of the proportion that have, let's say, this particular affliction or disease or condition in my population? So there's two scenarios we could look at. One is where you say, well, I would like my error to be 1%. That's the absolute, right? So I would like to be able to take that say, here's my estimate, and my error attached to that estimate is 1%. That's one scenario. And in the other scenario, it says, here's my estimate, and I'd like my estimate to be at most 10% of the thing I'm trying to estimate, P. So in one case over here, on the left, it says, okay, the standard error for my sample proportion is the SD of the box, which is the root P times 1 minus P, divided by the square root of the sample size. I'm ignoring the finite population correction factor. I'm assuming my population is very large compared to my sample size. And I would like it to be at most 1%. The other scenario says, all right, here's my standard error for my sample proportion, and same formula, but I would like it to be at most 10% of the thing I'm estimating. So in one scenario, where it's highly common, what's the bound that I'm saying that I want this to be? So with a 40%, roughly 40% incidence in my population, what's the upper bound I'd like on my error? 4%. And with the rare one, it's 0.4%. So those are the different ways or the different considerations that people make when they're trying in advance to figure out how large a sample they should take. Do you see why someone might want to use this scenario of taking 0.1% of P when you've got something really rare? Because you know, that 1% isn't that helpful if, you know, I'm going to create a confidence interval that might go from 2% to 6%. That could really make a big difference with what you're going to do with that estimate. So what I did is I used R. R is really handy. And I created a whole bunch of, I plotted the curve for each of these for the different P's. So in other words, the blue curve, I'm going to back up, but in a second. The blue curve is a standard error for my sample proportion based on different sample sizes. And the green curve is a standard error for different sample sizes as well, but it's when P is 0.04. So in other words, I just plotted these two curves. in one case, p is 0.4. Well, it's this one curve. In one case, p is 0.4. In the other case, p is 0.04. And so what's being varied is n, the sample size. Okay, so I have 0.4, the square root of 0.4 times 0.6 divided by the square root of the sample size, and that's what's varying. So it's a function of sample size, versus the square root of 0.04 times 0.96 divided by the square root of the sample size for different sample sizes. So you can see they both tail off, right? They're both getting smaller. The more I take, they're getting reduced by the square root of the sample size. But the green one is lower than the blue one because remember that p times 1 minus p, that function's largest at 0.5 and smallest when p is really small or really big. So focus in first on the absolute error. That's 1%. So that's this middle red line. So if your goal is to have 1% is your error, what sample size do you want to take? There's two answers to that question. One is it really a prevalent condition or is it a rare condition? So suppose it's suppose it's not a rare condition, it's a common condition. What sample size should you take if you want just 1% as your error? Yeah? Looks like, yeah, it looks roughly like 2,500. We look at this red line, go out here to see where it intersects the blue curve, and it's roughly 2,500. On the other hand, if we went at 1% for a rare disease that only afflicts roughly 4% of the population, we need only about 400. Okay, so let's now look at the other scenario where we want it to be 0.1 times p is the size of our error. So for the green curve, the rare one, that would be 0.04. And we follow out this bottom red line all the way out, and we see it's roughly 2,300 is the sample size we need. On the other hand, for the common condition, that's an error that's 0.04. And we see that we only need a sample of a couple hundred to get an error that's about 0.04. So when in advance, survey designers are trying to figure out how large a sample should they take, it's these kinds of questions that they need to ask. Well, how accurate do you want your confidence interval, or how small do you want your confidence interval to be? How accurate do you want your estimate to be? What size error would you like to have? And then there's always the trade-off of, well, that might cost a whole lot to do, and in which case that's often why things like cluster sampling come in. It can be cheaper to do a cluster sample than a simple random sample. And so those are the trade-offs. Any questions on that? So you can see how this the answer kind of depends on what's in the population, which you don't know, otherwise you wouldn't be taking your survey. And so you make rough guesses. All right. Last topic is the revisiting the 68% confidence interval. So I want to make sure that we know where this 68% confidence interval comes from. So I've created this little plot here, and I want you to take a look at it. Take a look at the label on the top. It says probability distribution of sample average. Okay? So question for you, is that the exact probability distribution of the sample average, do you think? What do you know from your experience with drawing these in R? Is that it? Yes?
This is just assuming that the sample average is normal.
It's assuming that the probability distribution of the sample average is normal. And we know that that's not a bad assumption when what? When the sample's large and not so large, right? It's large in absolute terms. This is this absolute relative thing again, but not so large in relative to the population size. So there's some assumptions going here to get this sort of idealized curve. The idealized curve of the probability distribution of the sample average says that it's roughly normal by our central limit theorem. And our central limit theorem is about drawing samples without replacement from the box as long as the sample size is large, but not so large relative to the population. It should roughly follow the normal curve. That red marker in the center, what's that? So what's the center of my normal distribution? The box average, which in this case, we don't know. So that's why there are no scales on this normal curve. I don't know what that is, otherwise I wouldn't be bothering to take a sample. So if the box average is the same as the population average, that's unknown. But we know, but one thing we do know, again, because we're taking a probability sample, we do know that it's the center of this normal curve. What's the gray area? With a normal curve? Yeah, somebody said it. I go up plus or minus 1%, or not 1%, plus or minus 1 standard deviation. And what's the area under the normal curve? 68%. So that says that the chance that my sample average is going to fall within 1 standard error of this probability distribution, 1 standard error of the population average is 68%. So this blue mark is my sample average. It's the one that I got from taking my sample from the population, adding everything up, dividing by the sample size. It's like what we did last Friday with those candies. A bunch of us took different samples. We each had our own sample, and we took the average of a 0-1 box and came up with a proportion of yellows in the population. Okay? So your sample could be over here, or it could be right there, or it could be out here. 68% of the time when we do this process, the sample average will be in that gray range. So now when I take that, notice that the distance from the red to the line, that's 1 standard error for the sample average. That's the same as the distance from the blue to the end of the confidence interval, which is the same as from the blue to the left end of the confidence interval. I go out, I take my sample average and I add 1 standard error for my sample average, and I subtract 1 standard error for my sample average, and that gives me my interval. Notice that the population average does fall in my interval. For which sample averages would it not be the case that my 68%, my confidence interval when I go out 1 and down 1 would not include the population average? Yeah? Which 32? So outside of that gray area. So if I'm down here, for example, in the left tail, and here's my sample average, and my confidence interval subtracts 1 standard error and adds 1 to create an interval, my interval won't reach the red mark. On the other hand, if I'm up there in the right tail, the non-gray part, and I create an interval by subtracting a standard error and adding a standard error to my sample average, my left end point of my interval won't be able to reach all the way down and include that red mark. That's going to happen 32% of the time. And the other 68% of the time, I will include the red mark. Now the problem is that we don't know, the only thing we see is is our blue mark. That's all we see, and our sample. And from that we construct this interval. Even constructing that interval, we make the assumption, which is a reasonable assumption, but we make the assumption that our sample SD is like our population SD. So we get this sort of approximate 68% confidence interval. It's approximate for a couple reasons. It's approximate because it's the normal central limit theorem says that that's the right distribution, and it's approximate because we don't know the true population SD. We've had to estimate it. And so based on that, I come up with this interval, and I don't know if this is one of those lucky 68% of the time and the population average is in there, or it's one of the unlucky 32% of the time and the population average is not in there. Likewise, a 95% of confidence interval, you can see that's when you go plus or minus 1.96 or 2 standard errors, and you get a much wider confidence interval. And you know that if you were to repeat this with the replicate function in R, which I showed you last Friday, if you were to repeat this many times, like 1,000 times, you'd expect 950 of those confidence intervals that you've created would include the truth, and 50 of them to not. But in practice, you've taken one sample, and you're sitting there and you're looking at it, and you take a sample average, you take a SD of your sample, you construct a confidence interval, and there it is. You present it, and you say, I'm 95% confident that the population average is in this interval. And that's why we use the word confident as opposed to probability. That confident is coming from this notion of, if I were to repeat this over and over again, 98% of the time, meaning the population average, would be in my interval. And I just don't know if this particular interval I'm presenting is one of those or not. Any questions? No? All right, I guess we're done for the day. I do want to say I've already started collecting data for or collecting more information for your projects. I'm going to start posting it while I'm just this morning, later on this morning. And if you've got something in particular you're really looking for, take a few minutes right now to come up and ask me about it, and I'll make sure that I address it.